What specific problem does the new method aim to solve in the context of large language models, LLMs?
The new method aims to solve the problem of high computational costs associated with large language models, LLMs, by reducing the number of layers required to predict each token during inference. This is achieved through a combination of layer dropout and early exit loss, which allows for exiting early during inference without the need for specialized hardware or software kernels. By enabling the model to exit early at certain layers, the method aims to create different-sized submodels within the same model, leading to faster inference without a significant drop in accuracy. The goal is to make LLM models more efficient by reducing the reliance on later layers and promoting the use of earlier layers for predicting tokens, ultimately saving computational resources and improving overall efficiency in deploying LLMs to various applications.
How does the proposed method work, and what is the training recipe that combines layer dropout and early exit loss? Illustrate step by step.
The proposed method works by combining layer dropout and early exit loss in the training process to create a self-speculative decoding approach. Here is the step-by-step illustration of the training recipe. 1. Layer dropout. The first modification applied is layer dropout, where during each training iteration, a dropout rate is applied to each transformer layer. The dropout rate can vary for each layer and iteration, with higher dropout rates for later layers and lower dropout rates for earlier layers. This is done to make the model less reliant on later layers. 2. Early exit loss. To boost the prediction accuracy of lower layers, early exit loss is introduced at each layer during training. This loss function connects the early exit layers to the language model, LM, head directly, supervising the lower layers for the language modeling task. The total loss of the model at each iteration includes the early exit loss at each layer. 3. Early exit loss curriculum. To prevent slowing down training and reducing the accuracy of the last layer, a curriculum for early exit loss is introduced. 2 curricula are explored: rotational early exit curriculum and gradual early exit curriculum. These curricula determine when to enable early exit at each layer during training. 4. Training process. The model is trained using this combined approach of layer dropout and early exit loss. The model is supervised to predict at earlier layers and exit early if possible, while maintaining accuracy. The training recipe aims to create different-sized submodels within the same model by allowing early exits at different layers. By implementing layer dropout and early exit loss in the training process, the model becomes more robust to exiting at earlier layers, enabling faster inference without significant drops in accuracy.
What are the theoretical or practical benefits of using layer dropout and early exit loss in the proposed solution?
The theoretical and practical benefits of using layer dropout and early exit loss in the proposed solution are significant. The use of layer dropout allows for stochastically skipping layers during training, which helps the model become less reliant on later layers and more reliant on earlier layers. This results in creating different-sized submodels within the same model, leading to more robust inference by enabling the model to exit early at different layers. Additionally, by applying early exit loss at each layer during training, the model is directly supervised to connect the early exit layers to the final LM head, improving the model's ability to unembed outputs from different layers. This approach ensures that the model can predict accurately even when exiting early, reducing the need for all layers to be utilized for every token prediction. The combination of layer dropout and early exit loss not only enhances the model's efficiency by reducing the number of layers required to predict each token, but also improves the model's accuracy by focusing on earlier layers for easier tokens and later layers for harder tokens. Overall, these techniques lead to faster and more efficient inference without sacrificing accuracy, making the proposed solution a valuable advancement in accelerating large language models.
How is the self-speculative decoding approach proposed in the paper different from traditional speculative decoding techniques?
The self-speculative decoding approach proposed in the paper differs from traditional speculative decoding techniques in several key ways. Firstly, the self-speculative decoding approach does not require an additional model or auxiliary layers, unlike traditional speculative decoding techniques that rely on having a separate faster model alongside the main model. This means that the self-speculative decoding approach reduces the memory and complexity requirements by using a single model for both drafting and verifying tokens. Secondly, the self-speculative decoding approach introduces a novel cache reuse technique that unifies the key value KV cache and storing the exit query, allowing for the reuse of hidden states in both the drafting and verification steps. This enables the self-speculative decoding approach to reduce memory usage and latency compared to traditional speculative decoding techniques. Additionally, the self-speculative decoding approach leverages early exit during training to generate draft tokens from the same model, and then uses the remaining layers to verify and correct these draft tokens in parallel. This differs from traditional speculative decoding techniques that rely on a separate, faster model to draft tokens and a larger, slower model to verify them. Overall, the self-speculative decoding approach in the paper offers a more streamlined and efficient solution by using a single model, introducing a cache reuse technique, and leveraging early exit during training, which sets it apart from traditional speculative decoding techniques that rely on multiple models and different architectures for drafting and verifying tokens.
What results were achieved in terms of speedups with the self-speculative decoding algorithm, depending on the model and task?
The results achieved in terms of speedups with the self-speculative decoding algorithm varied depending on the model and task. The speedups ranged between 1.341 number 1 and 2.161 number 1. Specifically, for the continual pre-training experiments with Llama 2 7B and 13B models on tasks like CNN, DM, and XSUM, the speedups were around 1.341 number 1 to 2.161 number 1. In the pre-training from scratch experiments, the bigger model achieved a higher speedup of 2.161 number 1 compared to the smaller model. When fine-tuning on code data with the Llama 1 7B model, the speedup reached up to 1.821 number 1. Lastly, in the fine-tuning on task-specific dataset experiments with the Llama 1 5B model, the speedup was 2.01 number 1. These speedups demonstrate the efficiency and effectiveness of the self-speculative decoding algorithm in accelerating autoregressive generation without sacrificing accuracy.
What are the limitations of the proposed self-speculative decoding solution, and what challenges are associated with the introduced hyperparameters?
The limitations of the proposed self-speculative decoding solution include the requirement to fine-tune or pre-train a model with the new recipe, unlike some other approaches that do not require changing the model's weights. This can be a limitation, as it adds an extra step to the training process. Additionally, the introduced hyperparameters, such as the layer dropout rate, 22-22, early exit loss scale, 44 number 44, and the dilation across layers for early exit loss curriculum, 39 number 39, need to be carefully tuned to avoid a drop in accuracy, which can be challenging and time-consuming. Tuning these hyperparameters, especially when pre-training from scratch, may require adjusting the learning rate to maintain accuracy, which can be tricky and may require extensive experimentation to find the optimal settings. Overall, these limitations and challenges highlight the need for careful parameter tuning and additional training steps when implementing the self-speculative decoding solution.